Alright, so today is our first video with a microphone, so this should be kind of exciting. I hope it's working. I'll find out, I guess, when I go to play it back. We're going to go ahead and continue with 2-6. So yesterday we did a little bit of 2-6. Today we're going to go ahead and try to finish up most of it. And this deals with horizontal, vertical, and slant, something called asymptotes. Okay, so first of all, let's talk about what asymptotes are. They are a line that a function will get close to, but not cross. Okay, there are three types, and one of them you've already been dealing with, even though we've not really named it as such. Whoops, there we go. All right, the first one is what you're used to, called a vertical. This occurs when the denominator becomes 0. Now, one thing that's interesting is that you can also, instead of just having a horizontal asymptote, you can have a hole, and we'll talk about that in a minute. I'm going to go ahead and list the three types, but I'm not going to define them right now. A horizontal asymptote is when, and you know what, I'm just going to, trust me, I'm just going to wait. And then we have something called a slant. Alright, we'll talk about these next two here in a minute, but let's go back to the vertical asymptote for a minute. Okay? So let's say I had a function x plus 3 divided by x minus 3. So it's going to have a vertical asymptote because it has a denominator. So you need to say that x minus 3 cannot equal 0, therefore x cannot equal 3. Okay? So at x equals 3 is the vertical asymptote. Okay? And I'll show you what they'll look like here in just a minute. But what's interesting is if we look at the function that's x plus 3 over x squared minus 9. So yesterday we learned that you can go ahead and factor that denominator. But I told you yesterday not to cross these out, that I wanted you to keep both of these in track. So yesterday you would have told me that x plus 3 could not equal 0 and that x minus 3 could not equal 0. So you said x could not equal negative 3, x could not equal 3. But do you agree that based on what you know from Algebra 2, these two binomials would cross out and just leave you with this? So this is not an asymptote, it's called a hole. So it's still a problem area for the graph. However, and in your domain, it's still going to look like what you saw yesterday. And quite honestly, if you don't quite get what a hole is, it's okay. Okay, you'll continue to improve on that when you get to PVCC pre-calc. Okay, but this point, x equals 3, is indeed a vertical asymptote. Okay? As long as you're using your domain's going to help you with your asymptotes. Alright, so let's do a quick example. So example 1 is going to look very similar to what you've been doing. It's going to say find the vertical asymptotes. And I'm going to go ahead and at least label them as an asymptote or as a hole. Alright, so the first function we're going to look at is x over x squared minus 1. So again, I have a denominator, therefore I know that I'm going to have a vertical asymptote. So I'm going to go ahead and I'm going to try to factor it. So how does x squared minus 1 factor? So it's a difference of two squares, x plus 1, x minus 1. So do you agree that these cannot equal 0? So x plus 1 cannot equal 0. And I realize some of you guys are to the point where you don't have to do this step here. I'm just writing it down again so that you have it. But by all means, if you understand it, so we know x cannot equal 1 and x cannot equal negative 1. So as far as though when I ask for the vertical asymptotes, they would be at x equal negative 1 and x equals 1. And if you graph them, you'll actually see that you do get that the curve is doing something interesting in between these lines. All right, number 2. Let's say I have function g of x equal to x1 over x squared minus 1. All right, so first step, let's factor that denominator. So again, you've got two factors, neither of which can equal 0. So I know that x cannot equal negative 1 and x cannot equal 1. But I want you to look back at the problem and decide, are these both asymptotes or is one a whole? So do you realize here these technically would cross out, which means this one, because he gets crossed out, becomes a whole. This is the asymptote. So I'm going to go ahead and clean that up. So we have a vertical asymptote at x equal negative 1, and we have a whole at x equals 1. Now on your calculator, you probably may not even see the whole, but we need to make sure that you understand it's there. And in class tomorrow, I'll go ahead and be able to show you graphically how this looks. But I feel like on the videos, the graphing calculator just doesn't do a phenomenal job. So we'll see. Let's do one more. And then we're going to talk about a horizontal asymptote. So first thing is, can you factor? So x squared plus 1 doesn't factor, but I know that because it's in the denominator, it cannot equal 0. So x squared cannot equal negative 1, and when I take a square root, I get again that x cannot equal plus or minus I, which is an imaginary root. So is it going to affect anything? No. So we have no limitations in the real number system, so we have no vertical asymptotes. All right, so you feel okay about vertical. Let's talk about horizontal then for a moment. So vertical asymptotes are the lines like this, vertical so that the curve stops. A horizontal asymptote is going to be a horizontal line that the curve will not cross. Okay? So it's all about the exponents of your function. So let's say you have a function a sub n to the x to the n divided by b sub m x to the m. Okay, these are just coefficients. Don't worry about those. It's all about these exponents here. All right? So here are the rules. Rule 1. If n is less than m, the numerator is less than the denominator, exponent. Then the horizontal asymptote is at y equals 0. Okay, so if your exponent in the numerator is smaller than the exponent in the denominator, you have a horizontal asymptote at y equals 0, which is the x-axis. Okay? if those exponents are equal. If n is equal to m. In other words, the exponents in the numerator and denominator are the same. The horizontal asymptote is at the line y equals the coefficient of the numerator divided by the coefficient of the denominator. Okay, the last one is if n is greater than m. In other words, the exponent in the numerator is larger than the denominator. Then you have no horizontal. And I guess one thing I want to make sure that I stress here is that the exponents you're looking at, are of the highest term. Okay? I hope you can read. For some reason I'm writing like a little chicken scratch today. Alright, so the exponents you're looking at are of the highest powered term. Alright, so let's try a second example, finding horizontal asymptotes, and then if we have time we'll put it all together into one problem. So find all the horizontal asymptotes. Let's say my first function is 9x squared over 3x squared. So you're looking at your exponents only. So I have x squared and x squared. So my exponents are the same. So go back to your rules. If n is equal to m, then you have a horizontal asymptote at y is equal to, take your coefficient of your numerator divided by the coefficient of your denominator, and I get y is equal to 3. Alright, number 2. G of x, 9x over 3x squared plus 1. Okay, it's all about your exponents right now. So the exponent in your numerator is 1. The exponent in the denominator is 2. So the numerator is larger than the denominator. So numerator is greater than denominator, exponent. So again, it's about the exponents, not about the coefficients. So therefore you have, let's see, here the numerator is less than. Please excuse me, fix your notes. So this 1 is less than 2. So if the numerator exponent is less than the denominator's exponent, you have a horizontal asymptote at y equals 0. I need to pay attention to what I'm doing. 9x cubed over 3x squared plus 1. Okay, last one. So again, look at your exponents. You have a 3, you have a 2. So the numerator is greater than the denominator's exponent. Therefore, you have no horizontal asymptotes. Alright, so the last thing we're going to do today is we're going to graph a rational function. And I'm going to give you some steps. Step 1. Find the x-intercepts. Do you remember how to do that? Set the function equal to 0. So set f of x equal to 0. Step 2. Find the y-intercepts. How do you find y-intercepts? You let x equal 0 and evaluate. Step 3. Find the vertical asymptotes. And I'm going to put if any, because it may not have any. Depends on, again, if it has a denominator. Step 4. Find your horizontal asymptotes. Again, if there are any. There may not be. I'm going to ask you to leave step 5 blank for just a minute. We're going to come in and fill in another piece to the puzzle, but not right now. And step 6, you're going to graph. Graph by hand. Step 7, verify with a calculator. Alright, I think we have time to do one, and then when you get to class tomorrow, I will work through a second one with you. Alright, example 3. Graph each function. So let's say my function is x to the 4th over x squared plus 2. Alright, so step 1. What does it ask you to do? Find the x-intercepts. Alright, so how do I find the x-intercepts? You're going to let the function become 0. So you're going to have 0 is equal to x to the 4th over x squared plus 2. So do you agree that first thing I want to do is get rid of that denominator? So I'm going to multiply this side by x squared plus 2. And if you multiply the right, you have to multiply the left. So now do you agree that these cross out and I'm left with x to the 4th equals 0 times x is 0 and 0 times 2 is 0. And now I take the 4th root of both sides, but I hope by now you see that x equals 0 is my x-intercept. Now, I don't want you to write it like this because that almost seems like a line. So I either want you to just say 0 or I want you to put 0, 0. Alright, are we ready for the y-intercept? So to find the y-intercept, you let x become 0. So find the y-intercept. And I apologize for the bell again. I'm trying to do these at lunch, but if I'm not exactly ready to start when the other bell rings, I get caught by a series of bells. So I'll see if maybe I can pause it before the next one. Okay? You let x equal 0. So you go back to your original function, and you plug in zeros. So we have 0 to the 4th over 0 squared plus 2. So 0 to the 4th is 0. 0 plus 2 is 0 over 2, which is still 0. So I have a y-intercept at 0. Or again, if you want to give it as an ordered pair, you can. Alright, find the vertical asymptotes. So the vertical asymptote happens when? It happens when the denominator becomes 0. So we need to say that this x squared plus 2 cannot equal 0. So do you agree that x squared cannot equal negative 2? And right now, do you see that you're going to have imaginary roots? Which means that this function has no points of discontinuity. Therefore, it has no vertical asymptotes. Alright, step 4. Find the horizontal asymptotes. Now the horizontal all depends on your exponents. So the power of your exponent in the numerator is greater than the denominator, therefore it has no horizontal asymptotes. And finally, I'm going to graph it by hand as much as I can, and I am going to go ahead and rely on the calculator quite a bit as well. But at least I want to see your x-intercept, your y-intercept, which this point are both the origin, and then I'm okay with you then grabbing a graphing calculator and sketching in the rest. If I had a vertical asymptote, it would go this way. A horizontal asymptote would go this way. But in this case, I believe we end up getting something that looks like a parabola. So on your calculator, go to y equals and type in x to the 4th divided by this denominator. Make sure you put them in parentheses, x squared plus 2, and verify your graph. And that's it. Sorry I ran late. I'll see you guys tomorrow. Have a great evening.